Binary search approach for longest increasing subsequence. In the last two lectures, we learned about longest increasing subsequence problem. And how did we solve this problem though? We solved it using dynamic programming approach. What we are going to do here is, we are going to see if there is any way to improve the time complexity of our dynamic programming approach. Looking at this heading, you may be feeling like binary search approach. It is probably not as good as dynamic programming because dynamic programming is generally supposed to be better. But it turns out that in case of longest increasing subsequence problem, binary search approach is better than the dynamic programming approach. Let us see how can binary search approach bring an improvement on our dynamic programming. First thing, in the last two lectures, what was the time complexity for dynamic programming? We saw that time complexity was order of n square. What is n here? N is the length of your input sequence. From your input sequence, you want to find the subsequence which is in increasing order and is the longest. What are we going to do now? From this order of n square, we are going to take this time complexity down to order of n log n. This is what we are going to do in this lecture. Let us see how is this obtained using binary search approach. First thing you have to understand here is, we are going to leverage binary search for this. And where are we going to use binary search? It is used to maintain a list of the smallest possible tail values for all increasing subsequences. What we are going to do is, we'll maintain a list. List you can consider as an array. What are we going to do in this array? In this array, each element will represent the smallest possible tail value. I'll explain what is this tail value. Smallest possible tail value for increasing subsequence which is having length of this index. If let us say index is 0, 1, 2, 3, 4, etc. then index 0 will represent the smallest tail value of a subsequence which is having length of 1. Index 1 will represent smallest tail value possible for a subsequence which is increasing and has length of 2. Similarly, each index I will represent the smallest possible tail value for an increasing subsequence of length I plus 1. So if the index is I, it will represent the corresponding subsequence length, tail value of the subsequence for a subsequence of length I plus 1. You have to clearly understand what is the difference between this structure that we are using here and the dynamic programming array that we used in the last lecture. When we used dynamic programming array, what did each entry in that dynamic programming array represent? Each entry represented what is the length of longest increasing subsequence which is possible ending at this particular element. This is what we considered while we were using dynamic programming approach. Clearly understand the difference between this DP array. This was our old DP array and this is a new binary search array. You have to clearly understand this difference. Once this difference is clear, rest of the algorithm will be very easy. What is each entry in a dynamic programming array? Entry at let us say ith index will tell you what is the length of longest increasing subsequence which is ending at this particular element, whichever is the element at index I. At that point, if there is any longest increasing subsequence ending, what is the maximum length possible for that subsequence? This is what a dynamic programming array used to tell us. So in that array, you just had to find whichever is the maximum element that will tell you the length of longest increasing subsequence. That was the logic there. But here, it is not about the length of longest increasing subsequence. Any particular entry will tell you what is the smallest tail value for an increasing sequence of length equal to I plus 1. This is the logic. Next thing is, what is this tail value? Why did I call it as tail value? I'm calling it as tail value because This will tell you if there is a subsequence that is having length I plus 1, then what is the last value possible in that subsequence. For example, if you have a sequence like something like this 5, 4, 8, 11, something like this, and you want to see that for length 2, what is a possible subsequence. From this you can see 5, 8 is a possible subsequence which is having length 2. Similarly, 4, 8 is also a possible subsequence of the sequence which is having length 2. Keep in mind, I am only considering increasing subsequences because our problem is longest increasing subsequence. Similarly, 511, this is also a possible subsequence. 811 is also a possible subsequence which is having length 2. Among all these subsequences, if you see the last values are 11 and 8. Among these last values, which is the smallest last value? 8 is the smallest last value. So that is what I will record in the index 1. So index 1 will tell you which is the smallest tail value possible for a longest increasing subsequence of length I plus 1, that is length 2. This is the logic. Whenever I am at any particular index, understand that for a subsequence of index I plus 1, I am talking about the smallest possible tail value, that is the last value in that subsequence. This is the logic. Next thing is, using this logic, how are we going to find actual longest increasing subsequence? This is the next thing. Let us understand this in detail. How are we going to learn this? So this thing is clear, right? I am going to erase this off. Whatever is the difference from a DP array and a newly formed subsequence binary search based array. Next thing is, how are we able to use binary search here? This is also a question. Generally, you want to do linear search if you have an array. In this case, we are able to use this binary search because we'll make sure that our tails array is always kept in sorted order. Because it is in sorted order, whenever you want to search for anything, you can directly use binary search. What is the advantage? Linear search will take order of n time, while binary search will take only order of log n time. This is the advantage we are going to get. Let us see the algorithm. So this will be a step-by-step explanation that will give you a clarity on where we are going to put all these pieces together. For now, I've explained you all the smaller pieces which we are going to use in the algorithm. Next step is, let us see how to use all these pieces, put them together in the algorithm and form the final answer. First step in the algorithm, what is the first thing you have to do? The first thing is you have to initialize an empty tails array. So I'll call it T. This is the tails array. Important point is this tails array should be empty. It should be empty. Why should it be empty? In previous cases, in a dynamic programming case, initially we had a DP array which is of size n and we initialized all the values to 1. But in this case, I'm telling you, you want a tails array, a list, but it should be empty for now. We'll add the elements as and when required, but for now it should be empty. Next step is, this is the most important step. Second step is where we are going to write the core logic. Here, for each element, let us say you have a sequence. You are provided with a sequence. For this sequence, so it will have some numbers like 5, 4, 11, 8, 13, something like this. For each of the elements in this sequence, what we'll do is, we'll use binary search to find the position where it can be placed in the tails array. You have a tails array. So I'll call this as the tails array. This is my tails array. Just imagine that I am already in the middle of my algorithm and I have some numbers stored here in the tails array. In that case, I am going to find out for each element by doing a binary search which is the right position to place this element in the tails array. From that, what will I do? First, we'll explain what we are doing and then we'll explain why we are doing. What is the logic behind this step? Okay. So first, let us see what we are doing. What we are doing is For each element I, what will you do? We'll do binary search on our tails array. Using this, we'll find out the position where this particular element, the ith element, can be inserted in the tails array. Then what will you do? In case the value of that element, let us say S of I, this particular element, if the element is greater than all elements in tails. For example, you have some elements in tails, or if it is initial condition where there are no elements, in both cases, this is the case when the element is larger than all the elements that are presently in tails array. If that is the case, what will you do? You will append this element to the tails array. So in case Si is greater than all elements in tails array, what should you do? You should append the value, that is S of I, the sequence, this particular element in the sequence should be appended to your tails array. Otherwise, if this is not the case, then what should you do? In case it is not greater than all elements, then during your binary search, you would have found a position. So that is the first element in your tails array that is greater than or equal to the current value. What are you going to do using binary search? Using binary search, you will find first element that is greater than or equal to whatever is your element. So your current element is S of I. Whichever you know, S of I is not greater than all elements, which means there is some element which is at least greater than or equal to Si. What are you going to do using binary search? Using binary search, you will find out the first element in your tails array that is greater than or equal to the current element. What will you do then? Once you find this, you can replace whatever is this first element that you found in the tails array. You will replace that with your current element S of I. This is the logic. And finally, what are you going to do? Final step is the length of tails. Whatever is the length of your tails array, that is going to be length of your LES. So finally, you will do length of tails. Next thing is, let us understand logic behind. You understood the step, what we are doing. Let us discuss why we are doing this. What is the logic behind this step? First thing is, what is the logic behind this step? Where if S of I is greater than all, then you are appending to the tails array. Keep in mind that whatever is the length of your tails array, that is the only useful information we are going to take from this. That is finally. Finally, when you want to see the length of LIS, longest increasing subsequence, you are only going to look at what is the length of your tails array. So that is the priority here. From that point of view, if you see, if all elements in your tails array are lesser than this particular element, then what does that mean? If you add this element to your tails array, you can increase the length of your longest increasing subsequence. You know all the elements are smaller, which means, and what does each point say? Each point tells you that there is a LIS, longest increasing subsequence, possible of length I plus 1, which is ending at this element. So you know, if let us say already there are 5 elements, you know for each of these 5 positions, it is possible to construct a longest increasing subsequence which is ending with this element. Plus, you know all these elements are smaller than your present element. That means if you put this present element here, which is larger than all these, you can take this sequence which is ending at 4, and what can you say? I know there is a sequence of length 5 and it is ending at some particular element, and that element is lesser than my current element. So I can add my current element to that sequence and make its length increase by 1. This is the logic. This is the logic of this step. What about the logic of this step? That is the else case. In case it is not greater than all elements, then what can you do? You should binary search and find out whichever is the first element in this list. This is in sorted order, keep that in mind. Whichever is the first element in this list that is greater than or equal to the current element. Let us say this particular element is greater than or equal to your current element. If it is greater than or equal to current element, what does that mean? This particular entry is telling you that there is a longest increasing subsequence of length 2 plus 1, 3 that is ending at this element. Plus, the element at which it is ending is greater than the current element. So it is a safe thing for you to say that if you substitute this particular element there, then you can say instead of the previous element which was greater than this, you can find a longest increasing subsequence which is ending at this element, the current element s of I, which is having length 2 plus 1, that is 3. This is the logic. This is why we are doing this. So you understood the logic now. Next thing is, let us write a pseudocode. So pseudocode will help you easily convert this into a code. This is why we are always going for the pseudocode. How will the pseudocode look like if you write this as a pseudocode? Let us say you have LIS, longest increasing subsequence of an array A. How are you going to find this longest increasing subsequence? As we discussed initially, you should know what is the length of array. This is n, which is the length of array. What should you have then? You should have an empty tails array. Tails should be empty. Next thing is, you have to go through each element. For I is equal to 0 to, what is the last element? If n is the length, n minus 1 is the last element. For each element, what should you do? You should do a binary search. Let us say index is equal to, you are doing a binary search to find position of that element. So find position using binary search. What are you going to do here? You are going to put it on tails array. On tails array, you are binary searching for the element A of I. When you binary search, what should you get here? You should get the smallest element that is greater than or equal to A of I. This is what it should return. Once you get that position, there are two possibilities. If all the elements in the array are smaller than this present element, it will return you position after the end of array. So if that is the case, that is if this index that is returned, this index, if this is equal to length of array. Length of array means position after the end of array, because last position is n minus 1. If this is equal to length of array, or you can say equal to n, if this is the case, then what should you do? Sorry, it should not be n, it should be length of tails. So I should write length of tails. We are not talking about array here, we are talking about the tails array. If index is more than tails array, that means you can append. That is the logic. So if it is equal to the length of tails array, then what can you do? You should do tails dot, you can append. To tails array, you are going to append the value A of I. Otherwise, if it is not equal to length, that means it returned an index which is somewhere inside the tails array. In that case, what can you do? You have to change that particular element. Tails array from tails array, whatever is present at that index, you should substitute it with your current element A of I. Finally, what should you do? Finally, how will you return length of LIS? Your length of LIS, that is the length of your common longest increasing subsequence, is the length of your tails array. This is the algorithm. What is the time and space complexity here? If you see the time complexity, this particular loop is running order of n times. Inside that loop, what are you doing? You are doing a binary search which will take order of log n time. After that, appending and exchanging values, these are order of 1 operations. So what is the total time complexity? Order of n times you are doing an operation which takes order of log n time. So your total time complexity will be order of n log n. This is how binary search approach is able to do it in order of n log n time. What about the space complexity? Your tails array is the additional space you are using. In worst case, what can happen? Your tails array can contain all the elements. If your input sequence itself is in increasing order, then all the elements in your input sequence will be present in tails array. In that case, your space complexity will be order of n. So your time complexity of algorithm is order of n log n. Space complexity is order of n. One more thing, a very important point before we conclude this lecture is that when I explain this algorithm, at least some of you could have had this doubt that the tails array you are having, this itself is the actual longest increasing subsequence. I told you specifically that the length of tails array is equal to the length of your longest increasing subsequence. But at least some of you may be thinking that this tails array we are having, this is also in increasing order. This is increasing order and it is also prepared by using the elements from the original sequence. So some of you might be thinking that whatever is the sequence present in this tails array, that itself is the longest increasing subsequence. This thought is wrong. Why is it wrong? The reason it is wrong is, yes, it is an increasing subsequence. Yes, it is having all the elements from the original sequence. But the problem is, for it to be a subsequence, the order of element matters. For example, if this is your set of elements 5, 3, 20, 11, 22, 33. If this is the, or 30. If this is the set of elements you are having, then 5, 20, 22. This is a subsequence. 3, 20, 22. This is also a subsequence. But 20, 11, 3, this is not a subsequence because it is not following the order that is present in actual sequence. Because you are using this binary search logic in tails array, what happens is, let us say at some point, just imagine you are having tails array like this. You have 5 here. Let us say you have, or let us say you have 3 here. You have 11 here. Let us say this is the current situation. And you have 20 here. 20 cannot come here. It has to be something else. 22. If this is the situation, and it so happens you are looking at some other element, let us say there is some element present after this which is having a smaller value, or you had some 22 here and you're doing a binary search for another element which came after this. It is possible that that element may take the position of 11. This is possible. I'm not saying it will always happen, but let us say at some point you have a element 8 and you did a binary search here. What will happen? 8 will get searched onto this 11. Then it will say 8 is smaller than 11 and I reached 11 is as the smallest possible element that is greater than or equal to 8. In this case, 11 will be substituted by 8. If 11 is substituted by 8, but 8 is occurring after all these in the actual subsequence you are having, what happens in this case? Here, 8 is coming before 22, but in your actual sequence, 8 is coming after 22. For this reason, whatever is present in your tails array, that itself is not the longest increasing subsequence. It can coincidentally happen that sometimes it may turn out that whatever is present here is actually the longest increasing subsequence. But ideally, you should not make this assumption. That is wrong. There may be many cases where the order is dismantled by the binary search, and because of that, it may not hold the actual longest increasing subsequence. It will always hold, one thing will always hold true, that is the length of the tails array, the length of your tails array, this will always be equal to the length of your longest increasing subsequence. So you should use this binary search approach only when you want to find just the length of longest increasing subsequence. For finding the actual longest increasing subsequence, you will have to backtrack on this algorithm. And this backtracking is easier if you use the dynamic programming approach, right? This is it about longest increasing subsequence.